Okay, perfect. So yes, once again, thank you to the organizer for organizing this very nice online workshop. And I said I'm Paolo from currently working in Vienna, and I would like to talk about this Planckian time of thermalization. So what it means and how it is related to metrology at thermal equilibrium. So let's start immediately with a bit of background. You see that if you take into account quantum mechanics is a theory that is governed by a scale of action, which is energy times time, which is h bar, which is the Planck constant. At the same time, if you take into account thermodynamics, via the Boltzmann constant, thermodynamics at any given temperature induces a characteristic timescale of energy. So you see that if you take quantum mechanics and thermodynamics together, there is at each temperature a natural time scale, which is given simply by this ratio here between the Planck constant and kBT. So for each temperature, we have a time scale, which sometimes I will be writing as beta h bar here. And this is what is called a Planckian time scale for temperature T. Now, the term Planckian timescale of dissipation or thermalization first appeared, as far as I know, in this paper by Zanen, in which essentially at the time people were a bit puzzled by the behavior of some superconductor with a very high critical temperature. And some empirical laws on the behavior of the conductance of these metals, they seem to suggest that at critical temperature or above, the electrons in these metals, they scatter or they dissipate with a characteristic timescale which was related or proportional exactly to this Planckian timescale. So by expressing the critical temperature in terms of quantum thermodynamics units, if you want. So this was a bit counterintuitive, and Zanet used this term for the first time. And then in following years, these kind of semi-universal behaviors of certain metals seem to be corroborated empirically. And so this led to the fact that at least in the theory of transport in models of insulators and metals, several models appeared trying to understand this diffusive behavior of charges in conductors and trying to claim the fact that this is indeed governed by scattering time or dissipation time, relaxation time, which is essentially the Planckian time. Okay, so this is a bit the status quo of knowledge, and this led a bit. So this was born again in the theory of metals, and this led to people conjecturing essentially that this Planckian timescale represents some kind of fundamental bound that appeared in metals, but perhaps is more general than that. There is also a nice review that you see here on the right, which you can read. And again, this is kind of conjecture to hold. So what I would like to present here is actually a proof of this conjecture in a specific framework that is operational and formal in the style of quantum info, a la quantum info. And it doesn't depend actually on the explicit dynamics that we are considering. So it doesn't depend on many body systems or metals, insulator. It somehow doesn't assume anything on the dynamical system besides quantum mechanics. So to introduce the idea in a pictorial way, we imagine a machine to be a thermalizing machine, if it is some kind of oven, if you want, in which you can regulate the temperature. And this machine, what it does, it accepts a system. So you insert a system with some given Hamiltonian, which maybe is initiated in any state that could be out of equilibrium. It's inserted at time 0 inside the machine. And then some time passes, and time tau, the machine is asked to return something that is somehow the thermal state at that temperature and at that Hamiltonian. So this we would call a thermalizing machine. If it gives you back something close to the thermal state in some sense. And this, if you can imagine, it includes the way global and local thermal baths work. the relaxation of subsystems or large many-body systems. But in general, we want it to be any entity, any machine, again, that is can be even highly engineered, that only has the scope of thermalizing your system. So this was the idea. In mathematics, the same idea is that we require this machine to satisfy quantum mechanics, which means that the state of the system that we insert at time t is simply given by the initial state that is put in contact with the machine, and then it evolves according to some Hamiltonian, some global Hamiltonian of state plus machine. And we don't make assumptions on the initial state of the machine, on the kind of Hamiltonian that the machine can implement, and the kind of interaction that it can have with the system. So it's fully general from this point of view. We only assume the local Hamiltonian of the system. And so this is simply, we don't know anything about what's going on, but just requiring quantum mechanics in the most general sense, if you want. And then we require thermalization, mathematically speaking, to hold in this way. So the state of the system at time tau should be close to the thermal state according to some distance, according to some possible error for some value of the Hamiltonians, which we assume here to be a ball of Hamiltonians for simplicity. So again, the state has to be close to the thermal state for some values of Hamiltonian. And again, this is the weakest possible sense, because this is approximate thermalization. It only needs to hold for a non-trivial region of Hamiltonians. Here it's just a ball for simplicity. We can also take into account the fact that time resolution might be finite, and also we might not be able to do full tomography, but only partial information. So this is somehow very minimal. I would claim as minimal as one can go. And with these two assumptions that I copy here for reference, what we are able to prove is that, yeah, any machine that does this job, following quantum mechanics thermalizes, has a time, an operational time that is bounded by exactly the Planckian timescale times a scalar. And this scalar has some formal definition. It depends on the distance that we choose, which is the Bures angle, the thermal state. It involves a maximization over the operators with some spectral seminorm. But besides the technical details, the crucial thing is that this chi is in general finite. It's upper bounded by 1/2. It depends on the kind of error that we require from the machine, on the generality of the thermalization. But crucially, what we find is that not only it is bounded by 0.5, but very generally is close to 0.5. So by very generally, I mean for all states that are essentially non-pure, that are not ground states. So we find that this is essentially always close to 0.5, and it only goes to 0 for very pure states, so for ground states. And summarizing in a very rough way, this means that the operational time of the machine is always bounded by this Planckian time divided by 2 for sufficiently mixed states with a spectral gap, capital delta here, that is not too big, while in the low temperature limit or very high spectral gaps, it's substituted by the adiabatic time scale. So this kind of makes sense. So here are some plots that show indeed the fact that these are all lower bounds to chi. I cannot go in much more detail than this. And they show anyway that chi is essentially close to 0.5, except when essentially the probability of the ground state of your system goes to 1. In this limit, it goes down to 0, substituted by this adiabatic time scale that I was mentioning before. So of course, I don't have time to give you the full proof, but just to give you an intuition of why this works, the idea is that we give the machine all the power that we want, but at the same time, still the machine needs to satisfy quantum mechanics, and it needs to distinguish different Hamiltonians that we might input in the machine. So, and also output thermal states that are distinguishable according to the thermal statistics. So if we input slightly different thermal machines, the variation of the input is going to be this delta HS for the machine. And in order to distinguish delta HS in quantum mechanics, you need a minimum time. So if you want, you can think of the limit of zero error, in which the machine is required to output exactly the thermal state at time tau, then any variation of the thermal state should correspond to a corresponding variation of the dynamical state, the output of the machine. And you can see that the variation of the dynamical state is governed by an order which is simply given by quantum mechanics, which is time, the variation of the Hamiltonian, divided by the Planck constant, while the variation of the thermal state is governed by this characteristic time scale. And so comparing these two, you can imagine how this Planckian time appears, at least in this limit. So this limit of zero error actually corresponds exactly to the limit of estimating HS. So it can be rephrased actually in terms of Hamiltonian metrology. I don't have time, apologies for this slide, but the problem of estimating Hamiltonians on thermal states is actually a limit of what I presented so far, and it's the maximization of feature information. So the optimization of metrology on thermal states, it's something that we solved actually in this previous paper here, in which we asked ourselves, given an Hamiltonian encoding of a parameter and some control on the Hamiltonian of a thermal state, how can we maximize the feature info? Well, we solved this problem here, and which you see in this line, essentially the bound, the maximum feature info that you can get for thermal states is given by this beta squared divided by 4 times the spectral norm of the variation of the Hamiltonian. And then this kind of completes a table of the optimal feature infos for dynamical encoding, thermal encoding, and in the limit also of encoding of parameters in ground states of systems. And simply, again, this is not a proof, but if you compare these quantities here, you can, again, immediately get an intuition of why the Planckian bound holds, simply by comparing the dynamical feature info with the thermal feature info in these regimes. Okay, so I will thank you for your attention. And to summarize, this timescale appears very naturally in quantum thermodynamics, and we prove that indeed it's the minimum timescale for a machine to thermalize thermal states or ground states. And we provide a formal operational proof of this. And this is kind of the intuition behind this comes from Hamiltonian estimation. And of course, you will find more details in the forthcoming paper. So with that, I leave you with the reference of the metrology paper and the hopefully forthcoming paper that we have been working in collaboration with Martí Perarnau, Pavel Sekatsky, John Calzamilla, and Alberto Rolandi. With that, I thank you.